Today I will discuss about the fourth chapter of class 11 NCERT, which is chemical bonding. Three types of bond are found. One is ionic bond, second one is covalent bond, and third one is dative bond. The octet rule is important for bonding of to understand the bonding in the preliminary stage. Each and every atom tries to attain 8 electrons in its valence while in bonded with other atoms. Like water, oxygen needs 8 electron uh, in its octet. For CCl4, carbon needs 8 electron for its octet, and also chlorine needs 8 electron for its octet fill up. In C2H4 ethane molecule, here also octet rule comes. It also explain the stability of the molecule. In chlorine, for chlorine gas, it also explain the stability of the molecule through octet rule. For nitrogen, it also explain the stability of the compound through octet rule. Lewis representation of some molecules. H2 Lewis representation is here given. O2 is given here. Ozone, one double bond and one single bond, and with a deuterionic mode. NF3, CO2, 2 minus, and HNO3, like this. Limitation of the octet rule: the incomplete octet of the central atom. In some compounds, the number of the electrons surrounding the central atom is less than that 8. This is especially the case with the element that having the less than 4 valence electron, for example LiCl, BH2, BeCl3. Lithium, beryllium and boron have 1 to 3 valence shell electrons only. Some others such as compounds AlCl3 and BF3, they have incomplete octet. Odd electron molecule: the molecules with odd number of electrons like nitric oxide NO, nitrogen dioxide. The octet rule is not satisfied for all atoms. For expanded octet, the element in the beyond of the third period of the periodic table, they apart from 3s 3p orbital, 3d orbitals also available for bonding. In a number of the compounds of these elements, there are more than 8 valence electrons around the central atom. For some examples, PF5, SF6, H2SO4, a number of coordination compounds have extended octet. It is clear that the octet rule is based upon the chemical inertness of the noble gas. However, some noble gases also, for example, xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like XCF2, KrF2, XCOF2, etc. Ionic or covalent bond. Ionic bond will be formed more easily between the elements with comparatively low ionization enthalpies and the elements with the comparatively high negative value of the electron gain enthalpy. Lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate one molecule of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of NaCl is 788 kJ per mole. That means 788 kJ of energy is required to separate 1 mole of solid NaCl into 1 mole of sodium plus gas and 1 mole of Cl minus gas to infinite distance. There are three types of radius: ionic radius, covalent radius and van der Waals radius. First one is here ionic radius, and second one is here covalent radius, and third one is the van der Waals radius. Van der Waals radius has the greater value of the magnitude. Bond angle, it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Bond enthalpy, it is defined as the amount of energy required to break 1 mole of bonds of particular type between two atoms in a gaseous state. The unit of the bond enthalpy is kilojoule per mole. For example, hydrogen-hydrogen bond enthalpy in hydrogen molecule is 435.8 kilojoule per mole. Bond order. In the Lewis description of covalent bond, the bond order is given by the number of the bonds between the two atoms in a molecule. The isoelectronic molecule and ions have identical bond order. For example, fluorine F2 and O22- have bond order 1, N2CO, NO plus have bond order 3. A general correlation and useful of the understanding the stabilities of the molecule is that with increase in the bond order, the bond enthalpy increases and the bond length decreases. According to the concept of the resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of the structures which have similar energy, the position of the nuclei, bonding and non-bonding pairs of the electrons are taken as canonical structures of the hybrid which describe the molecule accurately. For example, ozone molecule, the single bond distance is 148 picometer and the double bond distance to 121 picometer, but the observed result is found to be 128 picometer for hybrid structure. These are two canonical forms, and this is the hybrid structure of the ozone molecule. Polarity of the bond. The existence of the 100% ionic or 100% covalent bond represents an ideal situation. In reality, no bond or compound is either completely covalent or ionic. Even in this case, the covalent bond between the two hydrogen atoms, so there is some ionic character when the covalent bond is formed between two similar atoms. For example, H2O2 and Cl2N2F2. The shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called nonpolar covalent bond. Contrary to this, in case of heteronuclear molecule like HF, the shared pair between the two atoms get displaced more towards fluorine since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond is polar covalent bond. As a result of polarization, the molecule possesses the dipole moment. Dipole moment mu is equal to charge into distance of the separation r. The dipole moment is usually expressed in dBi, and dipole moment is usually expressed in device unit d. 1d is equal to 3.3356 into 10 to the power minus 30 coulomb meter. The bond dipole is like this and the resultant dipole is like this. For HF molecule, resultant dipole moment like this. For beryllium F2, dipole moment is 0. For BF3, dipole moment is 0. For NH3 there is resultant dipole moment. There is a resultant dipole moment. For NF3 resultant dipole moment reduced. Covalent character in ionic compound and the Fajans rule. The smaller size of the cation and the larger size of the anion, the greater the covalent character of the ionic bond. The greater the charge on the cation, the greater the covalent character of the ionic bond. For cations of same size and charge, D1, the electronic configuration N-1 Dn NS0, the typical transition metal is the more polarizing than one that noble gas configuration NH2 NP6, the typical of alkali and alkaline earth metals and nature. Cations. The cation polarizes the anion, the pulling the electronic charge towards itself, thereby increasing the electronic charge between the two. This is precisely what happens in the covalent bond. NaCl cesium chloride is ionic salt readily dissolved in water, but AgCl, HgCl2 are not considered as 100% ionic. The ionic and they are sparingly soluble salt. Now come to the main postulates of the VSEPR theory. The shape of the molecule depend upon the number of the valence shell electron pairs around the central atom. The pairs of the electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of the electron tend to occupy such position in space that minimize the repulsion and thus maximize the distance between them. The valence shell is taken as a sphere with the electron pair of localizing the spherical surface as maximum distance from another. A multiple bond is treated as if a single electron pair and 2 or 3 electron pairs of multiple bond are treated as single superpair, where 2 or more resonance structure can represent a molecule. The VSEPR model is appreciable to any such structure. The repulsive interaction of the electron pairs in the order. The lone pair repulsion is greater than lone pair bond pair repulsion, and lone pair bond pair repulsion is greater than the bond pair repulsion. For prediction of the geometrical shapes of the molecule with the help of the VSEPR theory, it is convenient to divide the molecule into two categories: the molecule in which the central atom has no lone pair, and the molecule in which the central atom has one or more lone pairs. This is the table for AB2E type of molecule. It is bent shape. AB3E type, where the number of bonding pairs is 3, lone pair is 1. So it is tetrahedral, but the shape is trigonal. Tetrahedral arrangement of the electrons, but it is trigonal pyramidal. Example is NH3. AB3E2 type lone pair, two lone pairs are directed in two tetrahedral corner and the shape will be bent. Example water. AB4E, and this is the example of the seesaw structure for SF4. For AB3E2 it is T-shaped, ClF3. For AB5E it is square pyramid, BRF5. It is square pyramid. For AB4E2 that is square planar XCF4. AB2E type molecules, another molecule is sulfur dioxide, bent shape, ammonia trigonal pyramidal, bond angle is 107 degree, deviated from 109.5 degree. Here one is Ab4E, which is CISO structure. Four types of structures are possible in which the CISO structure has more stability. Now coming to the valence bond theory and orbital overlap concept. The positive or in phase overlap of the two orbital along the axis will give a sigma bond, and the lateral overlap will give the pi bond. These are the example of the pi bond. These are the example of the sigma bond. And this is the example of the non-bonding molecular orbital, where the positive phase simultaneously overlap with the positive phase and the negative phase. So it is non-bonding orbital. Sigma bond. This type of covalent bond is formed by the end-to-end or head-on overlap of the orbitals along the internuclear axis. This is called head-on overlap or axial overlap. This can be formed by any one of the following steps: SS overlap, SP overlap, and PP overlap. And pi bond is the formation of the pi bond. The atomic orbital overlap in such a way that their axes remain parallel to each other, which is perpendicular to the internuclear axis. The orbital is formed due to the sidewise overlap of the orbitals. This is the pi bond. Sigma bond is stronger than pi bond. That's why sigma bond is stronger than pi bond. Salient features of the hybridization theory. The number of the hybrid orbitals is equal to the number of the atomic orbitals that get hybridized. Hybridized orbitals are always equivalent in energy and shape. The hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. These hybrid orbitals are directed in space in some preferred direction to have minimum the repulsion between the electron pair such that the stable arrangement occur. Important condition for hybridization: the orbitals present in the valence of the atom are hybridized. The orbitals undergoing the hybridization should have the almost equal energy. The promotion of the electron is essential condition prior to the hybridization. It is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbital of the valence shell can take part in the hybrid orbital. For sp hybridization, for sp2 hybridization, 3 orbitals participate. For sp2 orbitals participate, and for sp3 orbital 4 orbitals participate. It is the ground state of the carbon atom. It is the excited state of the carbon atom. Energy required for unpairing and promotion of the 2s electron requires some energy. That energy is called cost of hybridization energy, which must be satisfied by the bond energy. sp hybridized molecule BeCl2, sp2 hybridized molecule BCl3, sp3 hybridized molecule CH4 molecule, sp3 hybridized pyramidal NH3 molecules, sp3 hybridized bent water molecule. sp hybridized linear molecule, it has 50% p character and 50% s character, bond angle 180 degree. sp2 hybridized planar molecule, it has 33.33% S character and 66.66% P character, and bond angle is 120 degree. For sp3 hybridized molecule, it is tetrahedral, 25% S character, 75% P character, bond angle 109 degree, 28 minutes. Deviation in bond angle also is observed. For sp3 hybridized bent molecule, the deviation of bond angle is observed. Also, for deviation is observed for pyramidal NH3 molecule. Now come to PCl5. It is TPP shaped molecule. It is the ground state of the phosphorus atom. It is the excited state of the phosphorus atom. It is the hybridization of the S and 3p and 2d orbitals. This is sp3d2 hybridized. This is IF7 sp3d3 hybridized. This is sp3d2 hybridized SF6 molecule. Now come to molecular orbital. Molecular orbital theory was developed by F. Hunt and R. S. Mulliken in 1932. The salient features of this theory are psi mo is equal to psi a plus minus psi b. Therefore, the two molecular orbitals sigma and sigma star are formed. Sigma is equal to, with positive phase overlap, psi a and psi a plus psi b, and sigma star is equal to psi a minus psi b. The molecular orbital sigma formed by the addition of the atomic orbital is called the bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of the atomic orbital is called antibonding molecular orbital, as depicted in figure 4.919. The increasing energy, the atomic orbital psi a and psi b. Here is the energy of the psi a plus psi b, which is lowered, which is bonding molecular orbital, and psi a minus psi b, it is antibonding molecular orbital. Types of molecular orbitals. Molecular orbitals of diatomic molecule are designated as sigma, pi and delta. Sigma, pi and delta bond. Sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. If internuclear axis is taken to be in the z direction, it can be seen that a linear combination of the 2pz orbital of the two atoms also produce two sigma molecular orbitals designated as sigma 2pz and sigma 2pz star. It is the bonding molecular orbital of sigma 1s, sigma 1s star. This is sigma 2pz and 2pz star. This is pi 2px 2py. Now pi 2px 2px, and this is pi star 2px. Energy of the various molecular orbitals for oxygen and fluorine is given below. Sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than sigma 2pz less than sigma less than pi 2px is equal to pi 2py less than pi star 2px is equal to pi star 2py sigma star 2pz. For lithium 2, beryllium 2, boron 2, carbon 2 and nitrogen 2, the electronic configuration is sigma 1s less than sigma 1 star, sigma 2s less than sigma 2 star, pi 2px minus pi 2py less than sigma 2pz less than sigma star 2px is equal to pi star 2px is equal to pi star 2py less than sigma star 2pz. The molecular characteristics feature of this order is that the energy of the sigma 2pz molecular orbital is higher than that of pi 2px and pi 2py molecular orbital. Stability of the molecule. If the Nb is the number of the electrons occupying in bonding orbital and number of electron occupying in the anti-bonding orbital, then the molecule is stable if the Nb is greater than Na, and the molecule is unstable if Nb is less than Na. For Nb minus Na by 2 is equal to 2 minus 0 by 2 is equal to 1. Bond order. The nature of the bond. Integral bond order values 1, 2, 3 corresponds to the single, double and triple bond. For fractional bond order, there is a chance of the presence of odd electron in the molecule. Like example is NO, nitric oxide. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as the bond order increases. The magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic. However, if one or more molecular orbitals are singly occupied, it is paramagnetic. Like oxygen molecule is paramagnetic and nitrogen is diamagnetic. The bond order of H2 molecule is 1. For helium, bond order is 0. Thus, helium 2 does not form. Therefore, unstable. Lithium 2 for carbon 2 or oxygen O2. Bond order is 2 and its homo orbital pi star 2px and pi star 2py is singly occupied. Thus, it is 2 electron paramagnetic. Now come to hydrogen bonding. Hydrogen bond is represented by a dotted line. Hydrogen bond can be defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atom fluorine, nitrogen and oxygen of another molecule. The common example is HF. Here is two-dimensional hydrogen bonding by linear hydrogen bonding. Types of hydrogen bonding: intermolecular hydrogen bond and intramolecular hydrogen bond. Intermolecular hydrogen bond, it is formed between two different molecules of the same or different compounds. For example, hydrogen bond in case HF molecule or alcohol or water molecule, it is intermolecular hydrogen bonding. And second one is intramolecular hydrogen bond. It is formed when the hydrogen atom is in between the two highly electronegative atoms present within the same molecule. For example, orthonitrophenol is the example of intramolecular hydrogen bonding. There is a hydrogen bonding between the oxygen of the NO2 and the OH, hydrogen of the OH. Thank you. It is the end of the slide.